Right, hello everyone and welcome to the IET Midlands Power Group talk on managing the LV network constraints. Just a little bit of housekeeping first while people are still joining. So we have a Q&A button at the bottom. So if you need to ask any questions during the talk, please use the Q&A button rather than the chat function. The Q&A button just means that we can all see the questions and it goes into a template that we can use later on. The webinar will be recorded, and after this session, it will be uploaded onto YouTube for the Midlands Power Group account, so you can watch it later on. And the slide pack will be shared as well after this. So I know people will be asking if they can have the slide pack, and that will be shared to anyone who attends. So just to introduce our speakers today, I'm joined by David Mills and Owen Harris from EA Technology. David is an electrical engineer with more than 10 years experience working as a power systems consultant across a range of distribution networks, and in particular looking at how the networks will need to evolve to support decarbonisation. David is joined by Owen, who is a physicist with experience of renewable energy systems and data analysis, working to help the power industry understand the impact of various investment decisions. Today, they're going to be giving us an overview of a recent project looking into the options available for distribution networks to make sure the low voltage distribution networks that bring power to our homes are fit for a net zero future. So with that, I will hand over to David Mills to start his talk.
Thank you, Andy. Just load on the slides. Hopefully those have come up for everyone. Just someone can confirm.
Yes, they have. Yeah.
Thank you. So, £65 billion. By 2050, that's how much it's going to cost to upgrade the low voltage networks that bring electricity to our homes. That's £65 billion of our money. I'm David Mills, and I lead the net zero transition team at EA Technology. As Andy mentioned, I'm joined by Owen Harris, who is one of in the team as one of our net zero consultants. EA Technology's mission is to promote the development of resilient, accessible, and low-cost energy networks globally, and helping to accelerate the transition to decarbonisation. The net zero transition team are at the forefront of this and actively working with our clients to identify and overcome challenges on the journey to net zero through innovation, analysis, and justification. Today, we're going to talk through one of our recent projects we completed for the UK government in collaboration with Element Energy, looking at investigating some of the solutions to help manage the LV networks. And the aim of that being to find out what new technologies could be used to avoid spending that £65 billion of our money on upgrading the LV networks, but also making sure we can still support decarbonisation. So to achieve the UK government's net zero objectives, we will need to shift the source of fuel we use for heating and transport over the next 30 years. And two aspects of this, obviously heating and transport. So during tonight's presentation, we're going to look at what's causing electricity demand to increase and how that's going to impact the LV networks in the future. And then a bit more investigation into what those alternative options are and how they might roll out and how that's going to affect things. And some of that looks at what the problems are. We talk about electric vehicles. Maybe they could also help be part of the solution. So we all know electricity demand is increasing. We're talking about shifting transportation into electric vehicles, doing heating, so we're talking about the rollout of heat pumps. It's estimated that by 2050, we will be using 1.5 to 2.5 times the amount of electricity that we currently use. And as you might imagine, the electricity networks that supply our streets and bring power to our homes, not designed to handle all of that energy. So we talk about decarbonising transport. It's clearly going to have a big impact on the electricity consumption. This graph shows the forecast in uptake of electric vehicles between now and 2050. You may have seen in the press that the sale of electric vehicles last year was a significant increase at nearly 200,000. That's doubling on the previous year. But that still only represents 10% of all new car sales. By 2050, we're expecting, well, a long time before 2050, all car sales to be electric. But how does that actually impact on the power system? So an electric vehicle, based on some of the analysis we've done, projects that we've delivered, it consumes around 3,500 kilowatt hours of electricity each year. Thought we should give that a bit of context though. Why don't you put into the chat, who knows what the average consumption for a 3-bed house is? So anyone there want to type a number in the chat? Know what the average electricity consumption in a year for 3-bed terrace houses? Yeah, so we've got numbers 3,000, 4,000, 2,000 kilowatt hours. Some of you are good. 3,000 kilowatt hours. That's the estimated from Bayes on what the average house uses at the moment. So we're talking one new electric vehicle being the equivalent electricity consumption of a house. It's not just the annual electricity, it's how much we're needing at any one point. So a typical EV charger that's going in now, it's using a peak charging rate of 7.2 kilowatts. And that will charge your average car in around 8 hours. Now, there's been a lot of analysis that shows you don't actually need to charge the car every day, and you're not charging it from empty to full every day. So it won't be every car charging at that rate. But for a bit of context, your typical kettle only uses 3 kilowatts. And it takes 30 seconds to boil a kettle. But there's also heating. The second biggest consumer of energy is heating. And it's a big change to transition that to reduce our energy consumption going forward. Here's the forecast uptake of for heat pumps, either hybrid heat pumps or pure fully electric heat pumps between now and 2050. And the figure shows that we're looking to have nearly 25 million heat pumps installed by then. What does that mean for our electricity demand? So back to that 3-bed terrace house again, 3,000 kilowatt hours per year. The estimate for a reasonably well insulated house on a heat pump will use approaching 4,000 kilowatt hours for space heating, and then depending on the source for hot water, around 2,000 kilowatt hours. And the peak demand for a heat pump at 4 kilowatts, but there's already been some analysis on that. Obviously, not everyone's house will be heating at full rate all the time. Houses naturally have some thermal store. So once you diversify that, you're looking at an increase in demand of 1.7 kilowatts. Needless to say, though, still a big increase in the electricity consumption compared to what we currently use. So that's all looking at the individual house level. Obviously, the networks don't just supply one house, they supply aggregate houses, and there's some diversification going on. So when we start looking at how that builds up annually, this is the National Grid's future energy scenarios. In all cases, we're showing between 2020 on the left and 2050 on the other 4 bar charts, columns, depending on the particular uptake scenario, approaching a doubling of electricity consumption. And we should add not all of these scenarios actually achieve us getting to net zero. Steady progression is effectively what we're following at the moment, and that shows that actually we don't achieve net zero by 2050. In fact, we're a long way off. It's only leading the way that actually will get us there by 2050. In fact, it gets there just before 2050 and 2045, and consumer transformation and system transformation get us there by 2050. And obviously, for anyone interested, the future energy scenarios are on the National Grid's website, which gives some more details of how they come up with those numbers and the different assumed technologies they build into that. But they also give some information on the estimated increase in the peak demand. So depending on which scenario you follow, the chart on the left is showing the electric vehicle increase in peak demand. And this shows that even just by 2030, we could see an average increase in peak demand across GB of more than 7 gigawatts and potentially 15 gigawatts by 2050. And the same for heat pumps. By 2050, we're showing an increase of between 12 and 25 gigawatts in electricity consumption at peak times. Now, we're still going to get home from work, and we're still going to want to heat our house in the evening when it's dark and cold. And that's when we're going to want to charge our electric vehicles. So these are coming either at the same time or near the same time. National Grid estimates that by 2050, the peak electricity demand will increase from the current 58 gigawatts that it was last year or just before to around 100 gigawatts. And that's all the power that's got to come to supply our homes. Some of that's industrial use, but a large proportion of that is domestic consumption to your and mine houses. So we're going to need to upgrade the network. To get that amount of power to our houses, we're going to have to look at ways we can upgrade the network and avoid it becoming overloaded. So how do we make sure our distribution networks can achieve this? Well, the simplest way is just to go around replacing all the assets that are going to be overloaded over the next 30 years. It's following the sort of trend that we've had to do previously. Now, that's a lot of disruption. To dig up every street, replace it with a bigger cable. It's 400,000 kilometers of LV circuits as an estimate in the UK. And that's a lot of challenges. New substations as well, new HV network upstream to support that. And which circuits do we do first? And personally, I'd like to make sure that I could charge my car at home and heat my house on, so therefore it onto my street. But I'm sure you all feel exactly the same. So there's a lot of analysis needs to figure out where that would have to happen first. And how do you figure that out when people can buy an electric vehicle and plug in a charger when they want? Do we stop them doing that? Do we control that? These are all challenges that the networks are having to work with. And of course, if we're going to dig up every road, that's a lot of roadworks, a lot of disruption. Imagine every single street that you travel down during a day, at some point in the next 30 years, having roadworks, significant roadworks on it. And of course, it'll all come in clusters quite a lot of the time. But that's not the only challenge. Money, the other big challenge. Who's going to pay for all this? To give you some indicative values, a new LV substation is going to cost around £120,000. There's a lot of those. Slightly cheaper just to upgrade the existing transformers where that's possible. They're only £5,000 as an estimate, just to do a direct replacement. Now, in Western Power Distribution's region alone, which supplies some of the West Midlands, there's 50,000 of those transformers. That's £250 million just to replace them. And of course, all the new LV circuits. If we want to put a new LV circuit in, supplying a new housing estate or splitting existing circuits, that's £40,000. And of course, that's us. We pay for that, whether that comes through in central taxation or through our energy bills. At some point, it's us as users of the energy and users of the network that have to pay for it. So clearly, we need to find alternative options. And that leads me nicely onto the bulk of this project that we've delivered for BEIS, and looking to identify what alternative options are available to upgrade the LV network projects. So this made use of the EA Technology Transform tool. It's a techno-economic tool that allows us to investigate all kinds of different technologies and see which of those are most likely to benefit the grid and be rolled out in significant numbers. It's a representation of all of the UK distribution networks, input from the networks and from government, and looks at forecasting different uptakes of technologies to understand where the constraints appear on the networks, and then analyze those solutions to see which ones offer the greatest benefit in particular conditions. It's not a blanket statement for all networks. We have rural and urban networks, different types of network, different constructions. And part of this is done on an annual basis, looking at capital and ongoing operational costs, and looking at over the regulatory regime to understand how that rolls out. And we look at both obviously conventional solutions, so new transformers and overhead lines, along with what we call smart solutions, so other options that are available to us. So I'm now going to hand over to Owen Harris, one of our excellent net zero consultants working within the net zero transition team, and carried out a lot of the research, analysis, and endless hours of number crunching throughout this project. He's going to talk some more about some of the findings that we found out. Over to you, Owen.
Thanks, David. So you've just heard a little bit about how electricity demand is projected to increase and how that could cause some problems going forward in terms of financing these network upgrades and in terms of disruption that could cause. So now what I'd like to spend the next bit of this webinar talking about is a project that we did with Element Energy for the government to look at some smarter solutions to network reinforcement that could address some of those problems. So what did this project involve? Well, chiefly we did three things. The first thing that we did was we quantified the scale of the problem that this increase in demand and in the deployment of low carbon technologies was going to cause. And that's the £65 billion that David has already mentioned. And then next, we found some potential solutions to upgrading the network that could help us perhaps save on that 65 billion. And then finally, we quantified how much difference those solutions might make so that we could look at which solutions might be most important going forward. So on that first point, how did we go about quantifying the scale of the problem? Well, to take all the demand changes that David's been talking about into account and to look at how things might be in the future, we needed a quantitative and techno-economic modeling tool. And fortunately, we had one that we made earlier. And as David said, it's called Transform. So how does it work? Well, it has a lot of moving parts, the Transform model, but chiefly it needs three things. It needs demand scenarios and scenarios for generation and for low carbon technologies uptake, like the ones that David's been talking about. But it also needs network parameters, and that's because Transform is a parametric modeling tool. So rather than map where all the networks in the country are geographically and link them together, instead what Transform does is it focuses on a smaller number of network archetypes, and then it applies some statistical variations to those to create a wider pool of networks which are more reflective of the variation that you find up and down the country. And then Transform has detail on those networks in order to be able to model them. And some of the aspects that it has detail on are the thermal capacity of those networks and the voltage of the networks. Now, those parameters are very important, as some of you will know. Why is that? Well, it's because if the network's conductors or transformers run out of spare capacity, or if the voltage gets too high or too low, then we run the risk of having serious problems with our network components and ultimately with keeping the lights on. And what that means is that when the model's running and a particular network gets close to its limits, then the model has to be able to do something about that. The model needs a solution to fix a problem. And this brings us on to the third thing the transform needs. Because if, say, demand on a network increases in a certain year so that a network no longer has any spare capacity, then what the transform can do is it has a long list of possible solutions at its disposal, and then it can choose one to either increase the capacity of a particular network or to reduce the peak demand that that network sees. How does Transform decide which solution to use? Well, it has a long list of solutions in the model, and then they're all characterized by 29 different parameters, like how much the solutions cost, how long they last, how much headroom they might release, and so on. So Transform weighs the different solutions up and sorts them into a merit order for the constraint that it's trying to resolve. And from then it chooses the highest placed solution in the merit order or combination of solutions to fix the problem. And then what Transform can do is it can look at the cost of deploying that solution and all the other solutions it's deployed on all the other networks that it's modeling. And we can build up a national picture of what's going on, what solutions we're choosing to fix problems, and how much that's costing us. So now that you know that background, I'd like to tell you a little bit about how we use the model for this project. What did we do first? So we were interested in whether smart solutions could save you and I money, whether we could save on that £65 billion that David mentioned. So what we needed first was a counterfactual. We needed to know how much is it going to cost if we don't do anything about this, and if we don't find new smart solutions and we keep doing what David was talking about, we keep replacing conductors and transformers with larger conductors and transformers like we've done up to now. So this is the £65 billion that David mentioned. We got this by running the model for all the networks in Great Britain from now until 2050, all the different voltage levels, and we used those demand scenarios that show the increase in what's going on at low voltage. And what you'll notice here is that a large chunk of that expenditure is going on in the 2030s. So there's a significant step up coming very soon if we don't find some better ways of dealing with this increasing demand on the network and more low-carbon technologies that get deployed. So with nothing else at our disposal in this counterfactual, but the conventional solutions that we've always been using up to now, which solutions did the network choose to bear the brunt of this increase in demand and take us towards net zero? What I'm going to show you now is which solutions the model chose and how many times a year on average it needs to deploy those. So you can see here that there were 6 different solutions chosen by the model for the low voltage networks. And here the split feeder on the underground networks and the minor works on the underground networks and ground mounted 11 kV to LV transformers are solutions that are deployed by far and away the most. And in fact, those 3 make up 96% of all the deployments in this particular model run. So that means that for every 100 times that the model ran into a problem on a particular network, 96 of those times it chose one of these 3 solutions to fix that problem. So we're reaching really almost all the time for the contents of a very small toolbox to help us deal with these growing challenges. So where does that leave us? Well, now we know what we're up against. We're up against the £65 billion bill, and we know that it's primarily for tens of thousands of LV networks, which will need reinforcement every year. And these are particularly, you can see from this graph, underground networks. So not only is that a sizable increase in the portion of your electricity bill and mine, which gets spent on maintaining the network, but it's also thousands more roads that will need digging up every year. So it's a significant increase in the portion of our time that we spend waiting at temporary traffic lights. So do you think we can do better than this? Can we add some more cost-effective solutions to our toolbox? I think that we can. I think that what we're facing are new problems, so what we need are new solutions. And we're focusing on solutions at low voltage in particular, because of the challenges that we're facing primarily originating on the low voltage network. So we wanted to look at some smart solutions. We wanted to find what else is out there. There are some smart solutions that are already in the transform tool that we didn't allow the model to choose from in the counterfactual. So we've got those, but we've also wanted to search a little bit wider. So we undertook a literature review of smart solutions that might have come about since the transform model was first put together a few years ago. And now the bulk of this information came from innovation projects that the network operators in Great Britain have undertaken over the last few years. EA Technology has been involved in quite a few of those projects, so we had a good idea of where to start looking, but we didn't stop there. We looked at a plethora of other sources as well. And what we ended up with was a long list of different smart solutions, which we whittled down into a short list. And then for that short list, we defined the 29 different parameters the transform needs to put those smart solutions into the model. So what we ended up in the model with were the conventional solutions we've already met, some smart solutions that were already in the model, and some new smart solutions we found from our literature review. So what are these smart solutions that I've been talking about? Well, I don't have time to run through them all in detail. So I'm just going to talk broadly about the categories that they could be put into. So the first one I'm going to talk about are network side solutions. So these are solutions where the network buys a piece of equipment and installs it on the network, and that improves the parameters on the network. So in that respect, they're very like the conventional solutions that we've already met, only these are more dynamic. They change how the network operates based on conditions at the time. And as a result of that, these solutions rely a lot more on things like better network data and better communications infrastructure than we have on the low voltage networks at the moment. And then broadly within that, there are network side solutions that enable better use of existing network capacity, that connect networks together to reduce the load on the most constrained ones, and that mitigate voltage constraints. So those are the network side solutions, but what other types do we have? Well, we have some customer side solutions. So these are where electricity consumers, you and I, might buy something because we want to own it, and we want an electric vehicle, or we want a battery, or we want to have solar panels on our house. And then in these sorts of solutions, what could happen is the network compensate us for using what we've bought in a way that could benefit the network. And so most probably you don't need me to tell you that these types of solutions are becoming more prevalent, and they might become more important going forward. And then last but not least, we have solutions where a change to regulations could reduce the number of constrained networks by tweaking the limits as to how the network is allowed to operate. So where are we at now? Well, the question that we were asking was, will smart solutions save you and I money over reinforcing the network in the way that we always have going forward? And now we have everything that we need to answer that. We have everything we need to know how much it's going to cost with smart solutions and how much money that might save us. Because we have our model, we have all of our model inputs now, we have our solutions and our demand scenarios and our network parameters. And we also have that counterfactual to compare against, which I'll remind you of here. And this is with the £65 billion that it's going to cost us between now and 2050. So what do you think it might cost us between now and 2050, now that we've got the smart solutions as well? Why don't you open the chat and have a guess in there, if you're not too shy, on how many £billion you think it might cost us between now and 2050 with the smart solutions at our disposal, as well as the conventional ones. Let's see how much you think it's going to cost, whether you think it's going to save us not so much money or a lot of money. Fantastic, I can see some great guesses coming in here. I tell you about the prize that you can have if you get it exactly right, but unfortunately we haven't got one. Some fantastic guesses coming in there, thank you. So I'll put you all out of your misery now, right? When I ran the model for that, with smart solutions, it cost under £30 billion. That is a saving of over 50%, that's less than half the price. It's a bargain. For those of you that like to be precise, it's actually £28 billion, down from 64 billion. So it's a saving of £36 billion between now and 2050, or 56%. So the next question is probably comparatively more straightforward now as to where we go from here, because what are the smart solutions that could give us this enormous saving? I'll have to tell you about those now. So let's take a look at the solutions deployed by Transform this time. Remember, for the counterfactual, we looked at which solutions the model picked and how many times a year it picked them. Well, the first thing you notice about the results, including the smart solutions, is that we have a lot more of them, because before we only had 6 different solutions chosen by the model, but now we've got 17. So what that tells us is that we need a wide variety of smart solutions. Our toolbox that we keep reaching for has gotten almost 3 times bigger. And that's because many of our new tools are more niche. Some of these smart solutions, they're the best choice in specific circumstances, like on certain network types, or when used in combination with other solutions. What happened to our conventional means of reinforcing the network that I showed you earlier? Well, here they are, some of them. They're still being relied on in this run of the model, but in far smaller numbers than before. That's good news, because it's less temporary traffic lights for us to sit at while the roads are being dug up. But the fact that they are there, despite the proliferation of smart solutions, what makes what I think is an important point that I don't want lost in the discussion that we're having this evening, which is that conventional solutions aren't going away, and there'll still be times when they are the best choice. But you can see that it's the smart solutions that really dominate the deployments. There are 13 of them, but it's 3 of them that make up 73% of all deployments. So they're the ones that I'm just going to quickly expand on a little bit. So third, we have network data monitoring. So that is about identifying where there's spare capacity in the network, which can allow networks then to challenge generic design assumptions and run the network in a more informed way. The other thing that network monitoring enables is a lot of the other solutions on the list, because of the real-time load and voltage management information that you can get with network monitoring. So it's something of a win-win. But second, moving on, we have manual phase balancing. So what is that about? Well, that is about changing which supplies are on which phases for three-phase feeders. And this is one of those new solutions for new problems, because before electric vehicles and heat pumps came along, you were much more likely to have similar electrical demand to your next door neighbor. But now, as David was saying, if you have an electric car, if you have a heat pump and your neighbor doesn't, or vice versa, your electrical demand could be 2-3 times what theirs is at peak times. So that means that some of the phases in the network can be imbalanced, and that's a growing problem, which is why the model picks this very often as a good solution. But first, and first by some distance, as you can see in the graph, is behind the meter battery storage. So what do I mean by that? Well, that is one of the customer solutions that I was talking about. So that's people buying batteries, and then the networks, or by some other mechanism, they're compensated for using their batteries in a way that helps the network, like by reducing the peaks of their demand or of their export, or shifting those peaks to different times of day. And this is already starting to be incentivized by new types of things like time of use tariffs, which are reduced bills for changing when you use energy. And let's face it, energy bills are really on people's minds at the moment, understandably, and there's an appetite for finding new ways of reducing those bills. At this point, you might say to me, but Owen, that solution being deployed at that scale would involve hundreds of thousands of people buying batteries out of their own money over the next few decades. And that sounds a little bit far-fetched. And you're right in that it involves purchasing of batteries at a massive scale that we've not seen before. It's a radical change, but maybe it's not one that's quite as far-fetched as you might initially think. So just before I hand back over to David to talk about where we go from here in light of those findings, I'd like to leave these 3 things with you that we've learned, which is that using only conventional solutions, it would cost £65 billion to maintain the network to 2050. But if we use smart solutions and we use them well, we can less than halve that cost to £30 billion. And finally, batteries or electric vehicles can be the single most important solution at our disposal to help save us this money and avoid the associated disruption. Thank you. David.
Thank you, Owen. I will continue that. It's a great overview of how the deployment of new technologies will make it possible to operate the LV networks more intelligently. But what next? Clearly, this isn't going to happen overnight, and there's still a lot of work required across the industry to enable these solutions and other solutions to become technically efficient, commercially possible, and make sure we can actually achieve some of these savings that we've talked about. So one of the first points that we looked at there that's going to significant rollout is network monitoring. We've already got a smart meter rollout going on. That's obviously an enabler to a lot of these technologies. It allows people to shift their use of energy and be metered more dynamically, as well as new services that are starting to materialize. But the next stage of that is LV feeder monitoring. At the moment, we have very little monitoring that happens on our LV network. And so we're looking at how those get rolled out. An example here being one of the technologies, VisNets, but that's just collecting the data. Taking on from that, we've got to analyze it and model it, and there's continuous improvements in that area of ways we can better analyze that data and understand what's going on in the network. And with that, we then start to get other benefits, more accurately knowing the rating, the loading on transformers, monitoring the temperature. We can predict actual live loadings on those transformers and how close they are to what are typically assumed limits. And with some data analytics and some of the innovation projects that are starting to be delivered, there's ability to better predict faults, making sure that when early signs of faults appear, we can get out onto the networks and repair those cables at times when it doesn't take everyone's dinner off of being cooked, and we can plan that better. So these are all some of the benefits that start to appear along with these ability to better manage the network. And obviously, behind the meter energy storage was talked about, and we mentioned how that maybe looks like electric vehicles or people having batteries at home. But at the moment, it's still very expensive. Costs are reducing rapidly, but it's still got some way to go before it's affordable to all. And it may never be affordable to all. There's some people that in fuel poor categories, and that's a growing number with a continuous rise in energy prices. So there's definitely needs to change in the markets to make sure that people that can't afford to engage in some of these markets aren't left behind and picking up the bills for everyone else. And obviously making sure that these technologies can be installed in all conditions. People need to be able to charge vehicles or install batteries in their homes, and how there's changes in the technologies to make that possible. And at the moment, we're seeing across the networks growth in flexibility markets. Owen talks about time of use tariffs, which is all part of that. But they're still very complicated. A lot of them, I'd say, fail the sort of my parents wouldn't be able to understand that question. So there's some more work to go there. And they've got a shift to looking at the actual local network. At the moment, a lot of them are hooked up to the wholesale markets, and so you get cheap prices at those points. But if you want to use them to deal with just our local street level and allowing everyone on a street to balance, there needs to be some change in how those markets interface with monitoring. And obviously, EV charging is Electric Nation project was an innovation project that EA Technology delivered a few years ago. That showed the consumers are more than happy to change their charging patterns around relatively simple tariffs, or even just as long as it's automated and simple. And you're seeing or you may be aware that the government changed the regulations for all new chargers now going in for EV charging to be classed as smart chargers and have some of that capability. But there's still further to go in that to make it possible. So there you have it. Achieving net zero is not going to be cheap, and it is going to cost money for all of us, whether that's in our homes for our own energy use or in the items that we buy from shops. It's all linked together. And obviously, there's other challenges going on in terms of shortage and price rises, and that needs to be managed, and making sure that energy remains affordable as we go forward. And one part of that is, how do we reinforce the networks so we can both deliver net zero, but also save, just replacing everything and spending that £65 billion of our money. So using new technologies, we might be able to reduce that cost down to 30 billion. And finally, electric vehicles and batteries, and being able to shift the use of charging through markets is a key enabler to a lot of this technology. But the work's not done yet. There's a lot of challenges facing, and there's a lot of work that we're actively involved in to try and help solve that. How do we make sure that the networks of the future are resilient, accessible, and low cost for all? It's an exciting time to be in the energy industry, and we're actively working to try and solve some of these challenges. thank you for your time. The findings of this report will be made public at some point. So if anyone particularly wants a copy of the reports or the multiple reports, do drop us an email and we'll let you know when they're available. Other than that, if there's any questions, we'll be happy to take them.
Thank you, David. That was a really, really interesting talk. Thank you for that. There's certainly quite a lot of questions. There's 36 at the moment, so it piqued quite a lot of interest. Some fairly strong views on smart meters and their associated value and how worthwhile they are. So there's some questions on kind of the cost. You kind of mentioned 60 billion for the cost of upgrading the network in the start of your presentation, and a few questions centered around how much are people currently spending on updating the aging infrastructure already? So is that 60 billion on top of what they're already spending, or are they already spending 30 billion just maintaining the system?
So it's a good question. So that 65 billion is our forecast from now out to 2050 from a starting point. So that captures any replacement as a result of increase in load that is happening between that period. It doesn't capture things that might be replaced as part of aging infrastructure. The model isn't modeling that. So obviously, if something is aging and has to be upgraded, you don't replace it with like for like. You put in what you need for the future anyway. But we're not going to replace every transformer that we have, particularly by 2030, which is when some of this cost starts to occur.
Thank you. And with that update as well, there was a bit of a question around building regulations, and particularly with batteries and all the new houses being built. Are the building regulations keeping pace and ensuring that new homes are being built with the correct infrastructure so that they're not going to have to be updated in a few years' time?
So this is actually something that's quite, quite hardening. No, building regulations don't currently require a lot of this infrastructure. I mean, it's now, I think, a requirement they have to have the capability for EV charging. But there's a lot more that housing developers could do. The price point on PV and battery storage now is very close to being cost effective, particularly if you're putting that as part of a housing developer, you're going to get some economies of scale there. But obviously, housing developers are a commercial business, and if it's not profitable to them, they're not doing it. So there needs to be some regulations there to push that.
Yeah. Okay, thank you. And on the modelling side, so there's a few questions on modelling. Did the modelling consider larger scale localised battery storage connected at LV substations, or just domestic storage?
If I let Owen look at that one.
So not in this initial piece of work, but we have followed it up with a separate study into this after the results of this one. So we didn't have time to go through everything this evening. But as David was saying, if you get in touch with us, then once those particular findings are made public, then we can let you know them. But it was something that was definitely on our minds as we were doing this, particularly as we saw domestic storage coming out very favorably in the model. I think one of the points to make here is about the practicalities of network side storage as well, not just in terms of the space for networks to buy grid scale storage and install it, but also the regulatory mechanisms that are there at the moment, because at the moment it's extremely difficult for network operators to buy storage, because they then, if they're running flexibility trials and things like that, then they have conflicts of interest and they can't submit their own assets to be used when they're trying to store on the network and compensate other people for it. So it's another place where the regulations are not quite in keeping with where the technology is at the moment.
That's a really good answer, thank you. And I think that answers another question I saw come up, which is, how do you see the regulated role in this network reinforcement requirement? noting your comments about opportunistic reinforcement. So yeah, the regulator, how do you see their regulator's role?
So yeah, I mean, that's obviously, we did this project for BEIS, which will be setting policies that help drive some of the regulation forward, depending on how they interpret some of the findings. And yeah, the regulator, obviously the networks are going through their price control to distribution networks, going through price control to Rio 2 at the moment. So hopefully some of that will see some increases in aspects such as LV monitoring is certainly something we're seeing a lot of growth in. Recognition that before we can start upgrading the network, we need to know what's happening with it. And the regulators, obviously, they're currently in consultation on that, but we'll see in the next few months how they interpret those requirements.
And in the modelling, when you talk about batteries and behind the meter energy storage, what kind of capacity are we talking about? Kind of, and there's two questions really that I'm picking up on here. So one was, I guess, at the local level in my house, how much storage do I need? The other one was more kind of nationally, how much storage do we need to see?
So nationally, I think the answer is a lot. In terms of individuals, how the model works is that it's feederized. So it looks at individual feeders. So the amount of storage, it doesn't look at individual customers. So we're looking at sort of single figure levels of kilowatt hours per person. And then if that tops up over the feeder, then that is what the solution is trying to deploy, is many tens of kilowatt hours for a particular feeder. So if somebody has a larger battery and then some other people don't have batteries, then it's about how it tots up. And with regards to how much we need nationally, I think one of the interesting things with running Transform is how with certain networks, it'll deploy certain types of solutions, and with others it won't. So there isn't a sort of blanket of everybody must have this, but there will be areas of the country where networks are more constrained, where storage is more important.
Yeah, I think we should remember on that storage nationally is looking at two challenges. One is the part we're looking at here is local network constraints, but the other part of storage when you're looking at the national level is when renewables aren't available. So that short and longer term storage windows, which are different, effectively trying to solve a different problem, and that's largely where a lot of your grid scale storage comes in.
Thank you. And from this question's from me. On modelling, because I'm aerospace industry, does your modelling include the possible move of aerospace into electric vehicles and the eVTOL market?
So you mean with increased charging capacity for things like airports?
Well, so a lot of planes, there's a lot of talk about planes going fully electric or hybrid electric, much like the car industry did over the next kind of 30 years. So is that included in the modelling? It
will be if it's included in the national grid demand scenarios that we input into the model as part of this project. So the tool allows you to pick which demand scenarios you're modeling, basically. So you can look at different paths. And we looked at the government's CCC balanced scenario. So if it's in there, then yes, but off the top of my head, I don't know.
I think it's a very interesting question, Andy. It's something that we've been discussing within the team a little bit. And we're looking at rail decarbonisation is one aspect. We're doing a little bit of work looking at ships. But obviously aircraft is a different challenge because in the sense that the electricity demand for airports is already quite high before you then look at charging infrastructure. And I'm sure there's lots of work to do in that area as well.
Yes, absolutely. The power demand would be absolutely huge if they start to go that way. How are other countries tackling this issue, and what kind of solutions have they put in place?
So we're currently delivering a project for Tasmania and South Australia, looking at similar challenges. They're slightly different in they have huge PV uptake, and being much sunnier, they see constraints through that before they start to see the sort of vehicle side of things. So they're actually looking at how you manage the network the other way, and keeping effectively voltages down, and how you avoid reverse power flows on the network. And they're coming in with effectively how you create automatic voltage control schemes, curtailment windows. And when you start looking at curtailment of PV, that's effectively telling the customer they can't export, or should you have a battery, you might as well store that energy yourself, or if you've got a car, you charge it. So we come to a lot of the same points at the end, but from a different viewpoint to start with. So a lot of that is looking at again, advising their regulator on how they are going to invest in the network for the future.
So a few, I guess, less technical questions. Have you calculated how much this will add to the household average energy bill by 2050?
Sorry, the question, has it calculated how much that £65 billion goes on the household energy bill?
Yeah.
Yeah, I did that. It was scary. I did it again, and it was still scary. So I'm not sure how that's going to roll out. It was worked out at something like £2,000, £3,000. But obviously, that's only a very small component of the entire energy bill once you spread that out.
Yeah.
But obviously, we're still paying for our energy consumption. We're still paying for other transmission networking reinforcement, which isn't captured as part of this. So I can't give an exact number, I'm afraid.
I think another important point on that, when you're seeing what's happening at the moment with price rises, is context and the fact that this is something that we know is coming, whereas already there's a large portion of the bill that will fluctuate depending on the markets as it is.
Yeah, absolutely. And there was a suggestion that perhaps we should just increase the LV voltage and fit transformers closer to the property.
Yes, both very valid. Actually, we looked at the voltage as an option. That was one of the options we considered. Either whether you consider is increasing the voltage or changing the limits that you're allowed to operate within. That was one of the solutions. And yeah, shorter feeders will always help, and that's fine. But then we've still got to buy those transformers and put them in. I don't know, Owen, if you've got any more comments on the voltage ratio bit.
In terms of things like widening the tolerance, then yes, it's a question sometimes of unintended consequences to that as well. I know that a couple of years ago, the Energy Networks Association was looking at what if we what if we make it 230 volts plus 10 minus 10 rather than plus 10 minus 6, and what would the effects be there? And so they were looking at older appliances and seeing how many of those there are around the country and how many of those will break if we just decide to change the tolerances. And the answer was quite a few, but then it's a question of, is it easier to sort of pay for however many washing machines than it is to upgrade the network? So it's definitely an active area of things that people are thinking about. But a lot of the voltage control solutions are also quite expensive at those more automated scales.
And so we mentioned a few different technologies, and we've been focusing a lot on battery behind the meter during the questions. There's also obviously your domestic solar power, PV, and other things. Were they modelled as well?
They were modelled in that the increase in the uptake of them is in the tool, yes, but solar PV was not included as a solution to help with network constraints, whereas battery storage, because of its ability to smooth out some of those peaks or change when people are using energy, that's something that can help with network constraints and be effective in a different sort of way. But I understand that, yes, sometimes people having generation on their house, that's going to help.
Okay. But you don't think it's a significant contribution towards managing the network constraints?
Not actively.
Yeah, I think the challenge is there that a lot of these constraints will continue to appear during the winter when it's dark, and the PV isn't there for that. Obviously, if it means people can shift their demand to a time when it's sunny, that's the equivalent of having a battery. So you've kind of replicated the same benefit on the network.
So will this technology be available in time to be carbon neutral by 2050? So with battery capacity and production rates, will we actually be able to achieve this?
So the modeling assumptions were that we only consider technologies which are already available. So it's not like we're looking at anything which isn't either nearly or already available on the market. The challenge is the price point. And we've got cost curves that we assume for that price reduction. Whether it's actually manufactured in large enough quantities, I'd say is a market challenge. And if people go out trying to buy it and there's a shortage, more people will manufacture it.
I think there's another point there in that this is why the government was so interested in part in doing this study, because they don't want things like the solution not being ready in time to be the constraint that, as David was saying in his presentation, stops us hitting net zero.
Yeah, no, that's very good. Thank you. And I think we've reached our time, so I'm going to have one last question. I've not been able to make a dent in the questions at all, and we still have about 43 left. So we'll send these out to David and Owen to answer offline, and we'll send them around as much as we can afterwards. So I'll leave with the last question, which will be, what are the next steps for your project?
As Owen alluded to earlier, we're doing some further sensitivity studies looking at how these different types of batteries, different size grid versus end of feeder scale will affect it. And we're looking at some other sort of more novel technologies that we'd say aren't commercially available or near commercially available yet, to see if they have any significant depth, determining what the market size and opportunity are for those technologies, if they can get to the right price point.
Okay. Well, it sounds very exciting, and I'd just like to thank you and Owen for your wonderful presentation.
Thank you for having us.
Thank you.
I think, well, yeah, that's Martin.
Hi, yeah, so hi everyone, I'm Martin, the chair of the Midlands Power Group. I'm sure you agree that was a thoroughly fascinating insight into the new technology being considered to reduce rising costs associated with network modifications due to increase in load demand for EV vehicles and ground source heat pumps. What was really interesting to me was actually the sheer cost associated with potential network upgrades, and indeed the innovative solutions being considered. I know we've done questions, and I know we're running late on time. I did have one question myself, David, just very quickly. Other countries do, some countries do use three-phase distribution for domestic dwellings. Is that something we're going to potentially be looking at for, not for existing supplies, but maybe for future housing developments?
It's certainly being considered. I know new housing developments, there's a lot, or some of them are looking at, they're running three-phase to the meter and still taking one phase off, such that in the future, if there is a need to rebalance, that's much easier. And it's at the meter readjusting rather than having to dig up the cable termination, rejoint it. Whether we get to a full three-phase circuit around the house, I think it's probably a bit further away.
Thank you very much. That's great. So Just a quick reminder on CPD certificates. I know there were a couple of questions regarding CPD certificates. The IET, following the event, within the next week or so, the IET will send an email out asking you for general feedback. That will also ask whether you attended or not. If you're on this call, if you would like a CPD certificate, you will need to click and just let them know that you did attend. And then we then take that information and we'll generate the CPD certificate run. And indeed, with Dr. Mills' answers to the remaining questions. So on behalf of the Midlands Power Group, David, sorry, Dr. Mills, and Owen Harris, and I'm sure everyone else on the call, we'd just like to thank you for a great presentation tonight. And yeah, thank you very much. Very interesting.
Thank you. Thank you for having us.
Thank you.